This is the asynchronous video day that I promised you guys. This video is on content that's in section 1.3, so it's relevant to the 1.3 homework, but there also will be in D2L with the link that you got here, a couple of questions, very quick questions, just to make sure you watch the video. If you have issues with the questions, you always can refer back to the video. You don't have to memorize anything in the video. You can refer back as you want to. The concept that we defined in class on Wednesday was this idea of average rate of change, which I wrote down as a formula at the time that looks like this using the function notation. Now, we are continually looping through function notation, algebraic descriptions, and graphs in this course to make sure we understand the connections between all of those. So let me just say in words what this means from the point of view of functions, and then we'll see what it looks like, what it means in the context of graphs. So the numerator is measuring the change in the output of our function. In the example we did in class with the car driving on the turnpike, the function had inputs of time, what time it was, and the outputs were the position. So if you remember in the ones we did in class, our numerator was the change in position, the change in the mile markers. That's how far we had gone. The denominator for this calculation is the change in the inputs. And in our example with a car, our inputs were the times. So the change in inputs was the 1 hour that elapsed between the two measurements. So that's what we're always measuring, is change in output divided by change in input. Now, when we have a picture of the graph, so we have a picture of a graph of the function, then don't forget that the key relationship between function notation and graphs is that points on the curve, so this point, for example, has coordinate 2, 3, that is an input-output pair for the function. So when I identify that the point 2, 3 is on the graph, that means, from a function point of view, that f with an input of 2 has an output of 3. And notice I don't need to have an algebra formula for f to know that. Just because that dot is on the curve and has coordinates 2, 3, that tells me f of 2 equals 3. And then so similarly, the point down here has coordinates -1, 0. And so in terms of the functions, let me write that in a different color. In terms of functions, that means f of -1 equals 0. So again, that means when the function has an input of -1, the output will be 0. So that's how that's the really important relationship between the graph of a function and the input-output idea of a function. So what we're calculating then for average rate of change is just the change in the outputs divided by the change in the inputs. The outputs are the y-coordinates, so sometimes you'll see this written like this. It's the difference in the two y-coordinates that I have divided by the difference in the x-coordinates that I have. And it doesn't matter which point is which one. Normally, you will decide that the one on the left is the first point, and the one on the right is the second point, and just so you're always subtracting the bigger number minus the smaller number, but it doesn't really matter which one's which. So if we say the first point, the leftmost point, is x1, x2, x1, y1, and the other point is x2, y2, now we can just plug numbers in. The change in the outputs is the output on the rightmost point minus the output of the leftmost point. So that's 3 minus 0. That's the change in outputs of the function, which means the change in the y-coordinates of the points. And since I subtracted the 3 minus the 0, I then also have to subtract the 2 minus the -1. I have to keep these things paired correctly, so the point I'm putting first is this one over here, then minus the point that's over here. So once we write this down, we can sort of check to make sure I've got it in the right order. If this isn't the right order, then this input-output pair should go together. That's the output 3 for the input 2, and that's what I have. Here's the output 0 for the input -1. That's what I have. Okay, so those should go together. Now I just have to do the arithmetic. The numerator is 3. The denominator is 3 minus -1, which is, 2 minus -1, which is 2 plus 1. And so that is 1. So the answer to this question is 1, and I can get that by just drawing two dots and figuring out the change in the y-coordinate minus divided by the change in the x-coordinate. That is exactly the same idea as the measurement of slope of the line between them. The reason this graph has a dashed line here is so that we can talk about slope of this line. The slope of this line is exactly the same calculation that we did here. And that is the key idea in calculus, that the slope of the line calculation that we already know how to do measures average rate of change of a function. Okay, so that's the basic idea, and that's how we can work with it with graphs. There are a couple of problems on the homework where we're working with the concept algebraically, and those will feel different to you, so we'll make sure we do at least one of those. Before we do that, here's an example of a function where we want to find the average rate of change over an interval. So this is the first point. X1 is 1, X2 is 2. So on this picture, we'd want to draw the 2 points at the beginning and end of that interval, and then do a rise over run slope of the line segment that connects them. In other words, change in output over change in input. So I'm going to fill that in, and then we'll move on, but I'm not going to record while I fill it in. What you see appearing here is all of the same work that I did on the previous slide applied to this problem, and our answer was that the average rate of change of this function over the interval 1, 2, so over this interval, is 3. So check your work against this and make sure that you feel like that is the same thing that you would have gotten. Now, one of the first things you do in a Calculus 1 course when you talk about rate of change is you immediately change from the problem being about two particular numbers to having the problem be about one fixed point and then one point that involves a parameter, a letter. And that seems like a very harsh thing to do, but if we focus, we can do it exactly the same way. So here's the idea. I'm trying to do average rate of change from x equals 1 to x equals b. And so the b is unknown. The 1 is known. Right, there's the point 1, 1. That's the point we had a minute ago as well. And now I don't have any idea what b is, so I'm just going to draw it somewhere. But what I do know is that if you tell me that this x-coordinate is b, that means this point has an x-coordinate of b, and I know that every point on the curve satisfies this function's algebraic definition. So if you tell me the input is anything, the output will be that thing squared. So if the input is b, the output is b squared. So every point on this curve, whatever the x-coordinate is, the y-coordinate will be the x-coordinate squared. So we can actually write down 2 points over the interval 1 to b, and so I can use my average rate of change formula, which is the change in the y-coordinates over the change in the x-coordinates. The y-coordinates are b squared and 1. That's the y-coordinate of these 2 points. So b squared minus 1 is the difference in the y-coordinates, and the difference in the x-coordinates from here to here is from 1 to b. So the difference between these is b minus 1. So that's the average rate of change formula with when we use the letter b for our second point. And so that answer is fine. If you remember some algebra about the way that that can be simplified, you'll notice that the numerator can be factored and canceled with the denominator. But we don't have to worry about that right now. We'll come to that in chapter 3 later. But this would be a perfectly good answer. So we're not doing anything different. We just get an algebraic expression for an answer instead of a number for an answer. The problem that's a little bit harder is this version of it. And again, this is just a different version of the way you'll see this in calculus. But the idea here is I have a formula, an algebraic formula for this curve, and I want to find the average rate of change between 2 points. One of the points is over here. We say where an x is -1, that's where I'm going to start. So that is the point -1, 1. And then I'm going to put my second point at -1 plus something. And so that feels even weirder. But again, I don't really have to pick a number. I'm just going to put it someplace and just say, let's call it that. You can put it anywhere you want. Since it has a letter in it, it doesn't really, it doesn't really go anywhere in particular, but it does help to visualize it if you just put it somewhere and put a dot on it. A dot on the curve has an input of whatever that x coordinate is, and then the output comes from this formula. So now this is going to be a little bit harder to do. So I'm going to do it over here so I don't mess up my little space that I have for my graph. It will feel worse, but there's no hard calculation here. When you put a number in for x, that means you're just changing the x to be that whatever that number is. Right? That's what we mean by this. So if I put something else in here besides x, all I have to do is put that thing, whatever it is, in place of x over here as well. So instead of x in the formula on the right, I'll have -1 plus h. So all I've done is I've taken this expression and I've changed the x to be -1 plus h. That's what that's supposed to be. It runs into my curve. But that's -1 plus h. So in the denominator here, I have -1 plus h plus 2. And so that can be simplified to just 1 over h plus 1. And all I'm doing there is combining like terms. I have a -1 here plus 2. -1 plus 2 is +1, and the h remains, so h plus 1. So the reason for doing that calculation is that that is my output from the function, and so that's my y-coordinate of that point. And now I'm in business because I have labeled the 2 points. That's all that I need to be able to use the rate of change formula, is to have a representation for the 2 points. Average rate of change is the difference in the y-coordinates. So the outputs are, why did I not give myself more room? The outputs are 1 over h plus 1 minus 1. So that's this output value minus this output value. Right, so just the difference in those two output values. And then I have to divide by the difference in the input values. So the input value that goes with that first output is -1 plus h. And I subtract -1. So there's some funky stuff going on in the denominator that I need to pay attention to. This minus 1 is plus 1, but adding a 1 and having a -1 there kind of clears itself out. So in the denominator, everything cancels out or adds away and becomes just h. And then in the numerator, I have this. So this is a perfectly good answer. It can be simplified a little bit more if you wanted to, because we can do this subtraction if we're willing to find a common denominator between these two expressions. And then we could do something else with it. So it looks bad, but it is just the algebraic version of the slope calculation that we already did. So this would be a good answer to that question. So you can see that when we do this, that knowing the coordinates of the 2 points is really the key. And once we have the coordinates of the 2 points, we're just going to do the change in the second coordinate divided by the change in the first coordinate. And the change is always measured by just subtracting. So that part isn't too bad. When they're numbers, we can do the arithmetic, but even if they have algebraic expressions, we can still write down what the resulting algebraic expression would be. I'm not going to go into now why we would do this calculation in a calculus course. We might come back to that later when we talk more about the algebra going on here. But take my word for it, this will be the very first thing that you do in Calculus 1 or your applied calculus course is you'll talk about rate of change, and then you'll immediately apply the rate of change formula, this formula, to a problem that has a letter in it. And the reason for that will be clear when you get to that course.